Okay. Okay, thank you. Okay, so that's where we are. And if you think of even higher pressures, more dramatic things happen. So if you talk to astrophysicists, they believe that when they understand, nuclear physicists understand the equation of state of neutrons in a neutron star, and actually you get the superfluidity of paired neutrons in a neutron star. You may ask me, how do they know that, given and what kind of experiments they can do there, but I don't want to go there. The data comes from pulsar glitches, so it's somewhat indirect. But the estimated TC of this superfluidity is 10 to the power 9 Kelvin, which is a huge number. But look, the densities of neutron are also humongous in this compressed state of matter. So for instance, the Fermi energy of neutrons in a neutron star is 10 to 100 mega electron volts. So you can see that it's like more than 6 orders of magnitude larger than the density of electrons in solids. So perhaps it's not surprising. So there's a different way of plotting this data, which goes back to Tomo Uemura, which is called the Uemura plot, where instead of plotting TC versus time, you plot TC versus the Fermi temperature. Now, every experimentalist knows that you can hide a lot of sins in log-log plots, but you can also show a lot of data. So there is some use to it, okay? The vertical axis is well understood, critical temperature. The horizontal axis, we can have some arguments about, okay? Because if you have a simple parabolic band, then everyone understands what the Fermi energy is. But, you know, if you have a multi-band system, or if you have strongly correlated systems, we can argue what the Fermi energy in uranium platinum 3 is. So perhaps there's some error bar along the horizontal direction, but I don't think it takes away from the general trend. Now it seems like there's a desert here, and that's not true. This is the land of BCS superconductor. Now we can populate it with lots of stuff, which is not shown because we sort of understand that story. But then something interesting happens. There are bands on which things fall, okay? The green ones are the heavy fermions. The triangles are all putrates. And then there seems to be a real desert up here. But somehow there are no superconductors out there, okay? And the ones that come closest to that are magic candle twisted bilayer graphene, where also the definition of the Fermi energies could be problematic. We come back to that. Monorare iron selenide on STO. And actually, these are two ultra-cooled Fermi gas experiments. This one by Debichin at Gila, and this one by Wolfgang Ketterle at MIT. So actually, for these two data points, both the TC and the EF have been multiplied by 10 to the 8. So actually, the data points are down there, but they are definitely on the very close to this line. So this raises the question that is there some quantum mechanical reason why you could never have superconductivity in this upper triangle? And if there is such a reason, there are limits on TC, this putative bound should not depend on the mechanism of superconductivity, because these systems have absolutely nothing in common other than the fact that they are paired superfluids. Okay? So what I'm trying to convince you is that in this body of work over the last several years, we have produced rigorous upper bounds that give you insight into this for 2D systems. Okay, and many of them are 2D systems, magic candle twisted bilayer graphene monolayer iron selenide, and there are 2D cousins of these guys too. But as you will see, we do not succeed in producing such bounds in 3 dimensions. Okay, so with that, let me begin. So I think for this audience, I don't need to remind you that what happens in the BCS theory, what determines TC. Basically, you start with a normal metal, which is a filled Fermi sea with gapless excitations. You turn on a weak attraction between the electrons, get a pairing instability, and open up a superconducting gap. So you get a gap state. So the phase transition at TC involves 2 phenomena. One, the pairing of electrons. which leads to the binding energy of pairs and therefore an energy gap. Second, as soon as you form these Cooper pairs, you have a macroscopic condensate of these pairs, and that leads to all the super properties. So there are two quite distinct phenomena, actually, pairing and condensation, that occur together at TC. Now, the fact that TC should scale with the gap, you can put in numbers and so on, that's not so important. But larger the gap, larger the TC, is an absolutely central fact of not only simple BCS theory, but its generalizations, Migdal-Eliashberg theory, which include details of the electron-phonon interaction. This would suggest that the stronger the attraction, the higher the TC, right? Because the stronger the attraction, the larger the energy gap, and therefore the higher TC. But I think it's extremely important to remember that this entire framework works provided you have a series of inequalities. The Fermi energy is a huge scale, 1 to 10 electron volts. The Debye energy is an intermediate scale, which is maybe of the order of hundreds of Kelvin. And TC in conventional superconductors is of the orders of 10 or less Kelvin. Okay, so basically this ratio of the Debye energy to the Fermi energy, which is also the ratio of the speed of sound to the Fermi velocity, is the small parameter that controls Migdal's theorem and the entire Migdal-Eliashberg theory. And this is central to BCS theory in general also, even if you don't look at this. Now, this theory has been accepted to be a monumental contribution to all of theoretical physics. I mean, not just condensed matter physics. Okay? Nambu used the idea of spontaneously broken symmetry from BCS, took it to high energy physics. The Higgs mechanism was first discovered in BCS theory and then transported to high energy physics. Pairing in nuclei was something that people took from BCS theory and transported to nuclear physics. So this theory has had enormous impact for the last 70 years. But sometimes this is a psychological fact, when sometimes a theory is so beautiful and so successful that we are unable to look beyond it. And what I want to show you is that the present day experiments tell you that you have no choice. You must go beyond simple BCS ideas. So why is that? So let me give some examples. So this, I don't have references here. But if you look at very dilute superconductivity in Rhodes-Tromsø titanate, this is work of Kamran Benia, not far away. Then he shows that superconductivity persists down to the such dilute limit that the Fermi energy is less than the Debye energy. Okay, so certainly the Migdal parameter makes no sense. We don't really know whether this is an electron-phonon superconductor, yes or no, but you cannot use standard Migdal-Eliashberg ideas. Okay. If you look at the D-wave pairing instability in the Q plates, then this arises in states where Fermi liquid theory is not a good descriptor. Okay, near optimality, you have a strange metal with linear resistivities, ill-defined quasi-particles, all kinds of transport and spectroscopy signatures. On the underdome side, you actually even have a pseudo gap system in the normal. This cannot be described within simple framework of BCS theory. Okay. If you look at the cold atoms world, there people have realized using Fano-Feshbach resonances the BCS to BEC crossover in ultra cold atoms. And they have found experimentally, and these numbers come from the groups of, again, Checkerly and Debbie Chin, and actually in Paris, Christophe Salomon, and many others, okay, that the maximum TC experimentally measured in these systems is in three-dimensional ultra-cold Fermi gases near the unitarity limit is 0.22 epsilon Fermi. So this idea that TC has to be much less than epsilon Fermi makes no sense. It's a fraction of epsilon Fermi. Okay. Or let's look at superconductivity in magic angle twisted bilayer and trilayer graphene. I show some data from Pablo's group, but there's also actually work by my colleagues which is very similar. So here they're plotting in pink the coherence length as measured from the upper critical field. And they are comparing it with the interparticle spacing or KF inverse. And in BCS theory, the coherence length is huge compared to KF inverse, the Fermi wavelength. But in these systems, this ratio is of order 1. This cannot be described within BCS. Okay, so I think we have no choice but to actually widen our horizon if you want to confront these. I'm not saying that the same ideas will describe everything, but we just need to think beyond BCS. Okay, so what determines DC, right? So for the many materials that are very well understood within BCS Eliashberg, what you find is that the pairing is fragile, but the condensate is robust. Yes.
Please, one comment.
Yes.
Now, I won't say that this is very logic, what you tell, and very convincing, but I want to attract attention that BCS, which was created in 1957, gave us two pilasters. First, it is a gap in the spectrum, and which corresponded to Landau criterion of superfluidity and long-range order. And then already 3 years later, we started, the community started to refuse from some such statements. Gapless superconductivity. Gapless superconductivity. We understood that phenomenon of superconductivity can be even without gap, but supercurrent you have. And Berezinski, Taulis, Kosterlitz, where finally you refused from.
So I completely agree with that, Andre, but these are, in some sense, small deviations that people knew. These are huge things that we have no idea how to attack in some very systematic way. Yes, I agree with you. Yeah. So anyway, that's the story. But there is, for many relatively less understood superconductors, including the ones we discussed yesterday, although I don't want to discuss disorder today, the pairing seems to be robust, but the condensate seems to be fragile. It's just the opposite of BCS. Okay, in many of these examples, and you can go into why that is. And in all these cases, DC seems to be controlled by the superfluid stiffness, fluctuations of the phase of the condensate, even in completely pure systems. Okay, and so, as Andre just pointed out, this is very famous work of Berezinski, Kosterlitz, and Taulis. The Uemura plot actually was itself, in fact, Uemura was measuring superfluid densities in mu-SR experiments, so it originates from this kind of an. Yes, Ben. Yes.
It depends on what you define as DC, because what do you define? Is it the emergence of a gap like in BCS?
No. No. It's the thermodynamic phase transition below which superconductivity is seen as the DC. There is only one phase transition in these materials.
So it's R equals 0, that's the definition?
Fine, if you wish. Or superfluid density non-zero, even better. I don't think we disagree on what is TC. I mean, experimentally you may argue, but I mean, at a conceptual level, otherwise then why are we discussing superconductors if we don't know what superconductivity is? We understand what superconductivity is. Fair?
You were talking yesterday about superconducting insulators. So,
I was not talking about superconducting insulators. I was talking about paired insulators where the superfluid density was 0. They are not superconducting insulators.
Semantics.
It is not semantic. A phase transition is not semantic. A phase transition is a singularity.
The appearance of a gap is not a phase transition.
It is absolutely not a phase transition. Right? Why? Because it doesn't mean there's any thermodynamic singularity.
But you break
Or
kind of symmetry.
Say again, you have not broken any symmetry. Breaking a symmetry is a question of at least long-range order or long-range algebraic order.
So you are referring to some kind of non-analytic behavior as a phase transition.
Yes, that is what a phase transition is defined as, starting by Landau. And that is what Wilson also taught us when he developed RG. So I don't think it's a semantic thing. I think it's a very sharp distinction between what is a superconductor and what is not a superconductor. Just because you have a gaps occur for many systems. CDWs have gaps. We don't call them superconductors.
there's a transition to a CD that would.
But that's because you can see that transition in X-rays. That the symmetry of the system is different. So to me, this is not a semantic issue. The insulator I was talking about yesterday is absolutely not a superconductor. Otherwise, what are we talking about a superconductor to insulator transition if we think that the insulator is a superconductor?
No, you have pairs. So the thing
But that doesn't mean anything, right? That doesn't mean you have a phase transition. Like, okay, let me give you an example about pairing, okay? So suppose I take a gas of hydrogen molecules at room temperature, and I raise the temperature. Eventually, the molecules dissociate into hydrogen atoms. This is a very important phenomenon in astrophysics, in fact, described by the Saha ionization equation. This is depairing. H2 going to 2H. This is not a phase transition, but it is depairing of hydrogen atoms. Okay, so I do believe this is not a I very strongly believe it's not a semantic. Okay, yes. Okay, very good. So in fact, why are these two the ways of destroying superconductivity? Okay, that's because superconductivity involves an order parameter, has an amplitude and a phase. And the two ways to kill the order parameter could be either you kill the amplitude or you randomize the phase. Okay, and in fact, that's what these two are. So normally we think of superconductivity as an instability from a normal state. But if we think about TC coming from below, then whatever can kill you will kill you. Okay, in this side, the phase stiffness is very robust, but the amplitude not so much. So what kills you is breaking of pairs, loss of amplitude. On this side, the amplitude seems to be very robust, but the condensate seems to be very fragile. So what kills you is randomization of phase. Yes.
I have a simple question about fixation. You say that in BCS case, TC is somewhat like delta.
Yes.
And
scales with delta.
Yes.
Larger delta, larger.
Scales with delta, exactly. And you mean the order parameter delta, not the absolute value of delta?
I mean, yes, actually, I mean that because it's a real number, so I should put a modulus of that.
Thank you very much.
Okay, so now I actually want to think very carefully about this. Why? Because this tells you in this regime, TC is very, very strongly mechanism dependent. In fact, it's exponentially dependent on mechanism. But if you want to have some general story which applies to twisted bilayer graphene, to ultra cold atoms, to monolayer ion selenide, then you want to not think about mechanism. So let's look at the stiffness. So again, I don't need to go over the slide because I had it last. So for me as a case, this is what stiffness is. Okay. For an experimentalist, the stiffness is something you can measure either using penetration depth in 2D. There'll be a pearl length. You put the thickness of the film above it and get that. And another experiment that you can do is to measure the optical conductivity, particularly the imaginary part. Again, I emphasize that if you look at textbooks, they talk about superfluid density, but really there is no decomposition into numerator and denominator in general beyond one band parabolic dispersion. It's the package deal that enters theory and experiment. And also I want to emphasize that in general, it's not a question of normalizing, but it's just that these two objects are not related, the order parameter and the stiffness. They're just different objects. They are measured by different experiments. And I want to talk about things which are measured by these two experiments. Okay, so now that's the outline of my talk. First, I want to produce upper bounds in the first half of the talk. Second half of the talk, I want to talk about flat bands and topology. I may not say much about this experimental work done by my colleagues Jeannie Lau and Mark Wocroft. And then I do want to end with why this whole story does not work in 3 dimensions. So this series of papers largely arose from the PhD thesis of 2 graduate students who are now gone. Hazra is working with York Schmalian at Karlsruhe as a postdoc, and Nish Varma is a postdoc at Columbia. Okay, so let's start. Yes.
I'm sorry, I'm just confused about something you said about the stiffness. I'm not sure of how do you explain that it can appear both in the, you said energetical cost for fluctuations and in the penetration depth, whereas, penetration depth can be just explained by only London theory, very basic things without any fluctuation. And how can the stiffness
Okay,
appear
this
here?
will require me to sort of show you why those three statements are equivalent, which maybe we can do it in Q&A. But see, London theory is just a simple way of understanding it. It's a very good intuitive way of understanding it.
I try to explain it once.
Yeah, please.
You see, in penetration depth, you need a current, shielding current.
Yep.
And the current can only flow if there's a phase twist.
Yeah, okay.
And if the energy cost for a phase twist differs, then the region in which you can get that given phase twist differs.
To me, this is not fluctuation.
No,
It doesn't have to do with fluctuations. You
You
can just
have to turn phase
how
with
much
the current.
energy does it cost to twist the phase?
Exactly.
It doesn't have to be a fluctuating.
Phase stiffness is high, then you need a large range to twist the phase by a given amount, and the penetration depth is large because the current has flow over this large range.
So this I understand, but then I'm confused with the first assumption with the fact that the cost for fluctuation is
It's not fluctuation. It's the cost for imposing a gradient in the phase. Think
okay.
about it that.
Yeah, okay. Thank
Okay? And that'll help you. Okay, very good. Okay, so let's get started. Actually, there's no better thing than to have a student explain to another student, because then you know.
I cannot take credit.
Yeah,
this is how it was explained to me like 2 weeks ago.
Thank you. Okay, so we want to prove some very general results. So here's what we'll do. We'll say we have some arbitrary band structure, and we'll focus on a low energy Hamiltonian which says ignore all the completely filled bands and completely empty bands, and focus on the bands near the chemical potential which are active and going to be impacted by superconductivity. So you can just have an arbitrary dispersion. So M is a band index. You can have as many bands as you want. K is the crystal momentum, and sigma is the spin. Okay, and I don't want to commit to any interactions. Okay, so let's have an arbitrary interaction. It seems like, what can you do with this Hamiltonian? All Hamiltonians more or less belong to this class. Okay, so I will make one assumption. So you want to prove a theorem, you have to state what your assumptions are. So this one assumption is a crucial assumption. Since we want to calculate the penetration depth or stiffness, which is the response to a vector potential, we should ask, how will the vector potential couple into this Hamiltonian? I would say that the vector potential couples only to the kinetic energy, but not to the interaction term. So in the continuum, this is absolutely clear because P goes to P minus EA, minimal coupling. Or on a lattice, you get the Pyle space factors. Okay. So now you can ask, is this assumption restrictive or is this assumption reasonable? Right? But this is the assumption I'm going to make. So the answer is, it's definitely true for 99% of the systems that I know of. So electron phonon, Holstein models, Hubbard models, TJ models, density, spin. It's also true in ultra cold Fermi gases where A must be, okay, there's some dictionary which says rotation is like vector potentials. Okay, so it's definitely true that the vector potential only couples to the kinetic energy and does not impact the potential energy, whatever it be. You can ask, can I find counterexample where this assumption fails? And the answer is there are two cases which are quite important to present day literature where it does fail. Okay, and let me state immediately what they are. So first, people are thinking about flat band superconducting. But a flat band means you have no kinetic energy. If you have no kinetic energy, then you can't say the vector potential couples to it. So this assumption would fail. Second, if your bands are topological, then actually you cannot write down a simple tight binding model just for those bands, because topology acts as an obstruction to getting exponentially localized Wannier functions. So these are very important exceptions, but maybe there are 2 or 3 experimentally relevant superconductors where they might be valid. In the second half of my talk, I will come to that. Right now, please forget this, and let's just say that the interaction, the vector potential couples only to the kinetic energy and not to the interaction. Okay? Very good. So now, there's a standard way for calculating the stiffness, and the classic reference to this is Gordon Bain, 1968. A more accessible reference to it is Scalapino, White, and Zhang in the 1990s. So you do a Kubo formula to calculate the transverse current-current correlation function. I think you don't need to know, if you are not familiar with this technique, you don't need to know about it, okay? Because I'll explain the content in a very simple way. It has one term, which is d tilde, and it has a second term, which is the transverse current-current correlator. That's the hard piece, but you can just do a Lehmann representation and argue that the second piece, which is hard to compute in general, is positive definite. So you get an inequality, which is exact, valid for arbitrary interactions in any dimension, that the superfluid stiffness is bounded by the first term. I'll give you a very intuitive experimental way to think about this inequality, but I want to make sure I tell people that we can prove it, okay? ds is bounded by d tilde. Now you ask, what is d tilde? This is just some symbol, what does it mean? So I explain immediately what it means, okay? So 2 ways to think about it. One is it's the diamagnetic piece, because current has 2 pieces, a diamagnetic piece and a paramagnetic piece. The other and even more physical way to think about this d tilde is in terms of an optical summary, okay, which in some contexts is often called Ferrand-Kungla or something. So if you look at the optical spectral weight of just the active bands, so integral g omega over the range of frequencies of the active bands, the real part of sigma omega, that is d tilde. So d tilde is a gauge invariant physical observable that upper bounds it. Now, sorry, I skipped the picture, but maybe I can draw it here. I seem to not have that slide there. So in an optical conductivity, what happens? If you plot the real part of the optical conductivity, okay, then it has a delta function at the origin, and then it may have something, I don't know, whatever, some other. Okay. Whether it's fully gapped or if it may be a superconductor, there would be other stuff. It doesn't matter to me what there is. Okay. Now, d tilde is basically, you're calculating, if you want to, so you basically, d tilde is the total weight. Okay. So all I'm saying is that the weight inside the delta function has to be less than the total weight. How much weight can you, what is the maximum weight you can condense into the delta function? That which was available to you in the total optical space. You can't condense more into the delta function than was available to you. That's the intuitive content of the algebra that I showed you. Thank you. Now, how do we compute it? Here is d tilde. And okay, I don't know, maybe there are, we can save this for the Q&A, but there is, you give me a band structure and I can write down a formal expression for it. Remember we said that all these objects, superfluid stiffness, optical spectral weights, look like a density divided by the mass. But what it turns out to be is actually a density matrix times an inverse mass matrix. You give me the band structure, I can calculate for you the inverse mass matrix. But we have to remember that this expectation value actually depends on trace e to the minus beta fully interacting Hamiltonian. So it depends in principle on interactions and temperature. Okay, so what have we technically achieved? You see, the stiffness was a current correlation function, which is like a 4-point function. We have bounded it by a C dagger C. which is a much easier object for theorists to control. Now, where does this lead us? Okay, so up till now, everything I had said was valid in any dimension. Now I come, because I'm in TIDES, to 2 dimensions. Okay, so in 2 dimensions, we've heard in many beautiful talks earlier that you have the BKT transition from the superconducting state to the normal state. Now, I was glad to see, Andre, that you also had the same picture of Berezinski, because I got it from the internet, but I wasn't sure whether this was a fake picture or a real picture. But it seems it is you, since you knew him, this must be the real picture. Because I think he died very young, unfortunately.
42.
That's right. So otherwise, he too would have received the Nobel Prize with Koskins and Thomas. Okay, so we know this physics. It's the unbinding of vortex-anti-vortex pairs. So it's the phase disorder which is making this non-superconducting normal state. Okay, and since this BKT-TC is determined by the balance between the entropy and energy of vortices, you can see that TC is going to be scaling with ds here. Now, this is not just a tilde. There is a very precise calculation that you can do. It was done by David Nelson and Koslitz, which said that actually the superfluid stiffness has a jump discontinuity. Okay, and the stiffness just below TC, because above TC it has gone to 0, is actually related to TC itself by a universal constant pi/2, which does not depend on any material parameters. The universality of this pi/2 is very crucial to our story. Okay, and maybe in Q&A we can discuss why is this pi/2 universal. So then our bound proceeds as follows. It says TC is related to the stiffness just below TC. But I told you that the stiffness is upper bounded by the optical spectral wave. So TC cannot be larger than this object. Now, it's not clear that this is a useful equation yet. The rest of the talk is going to try and show you how it's actually very useful. But one thing is clear, this is an exact statement. No mean field theory. It's independent of pairing mechanism or strength, so long as you have a BKT transition. And it's independent of whether the normal state is a Fermi liquid or a non-Fermi liquid. It's just independent of almost anything that can be. Okay? Now the question is this just some theorist writing some useless equation on the board, or is it useful? So what I'll try to convince you is that when we have low densities and narrow bands, okay, then this is a very small number which constrains TC. So it is very useful. It's particularly useful, I'll show you, as a complement to BCS theory. Where mean field theory fails, this shines. And where mean field theory works, which it works for many systems, this is still a true result because it's an inequality, which is exact, but it's pretty useless. Okay? So let's try to understand that in detail. So to understand this, we will go over a series of stress testing this inequality, from parabolic bands to cold atoms to lithium doped. This should be zirconium nitrochloride. There's no P here. Iron selenide, twisted bilagraphene. Let's just go through it. So when you have a complicated result, always look at it in the simplest limit to start with. So let's take a single parabolic band in 2 dimensions. Put any interaction you want. That will give you superconductivity. Okay, so dispersion is k squared, density is n. This is Fermi energy in 2 dimensions. You put it in a formula, and you find this remarkable result that no matter what you do, you can never raise TC about 1/8 epsilon Fermi, ever. Okay, so you can plot 1/8 epsilon Fermi, and at least for a little while, you can rejoice that all the data falls below it until reality hits at you. And yes.
So here, this theorem epsilon Fermi, it only considers the bands that participate in superconducting.
Yes.
And in real materials,
We've come to multi-band systems, so just hold on. We have to go from the simplest to the harder cases. Yeah, so I think the real problem is the following, that most of the systems are not parabolic. So what happens in non-parabolic bands is the first question to answer. What happens in multi-band systems is the later question to answer. And I will address all of those issues. Okay. One thing is clear, that this is like Druder model. You know, it's like a spherical cow. It gives you a flavor for what happens, even if it may not be exactly what happens in life. Okay. So it tells you that something like this may be true, but before we get to all those complications, let's ask, are there parabolic systems in the experimental world where this can be tested? And if so, how does this work? Okay, that's a fair question before going to the kinds of questions you're raising. Okay, so then this is the story of the BCS-BC crossover, because I thought that this would be the first place it would be tested. It turned out not to be, but that's okay. So this is the story that in ultra-cold atoms, you can actually tune the interaction in the lab, which you can rarely do in the solid state, and go from the regime of BCS theory with huge Cooper pairs compared to the interparticle spacing to a Bose-Einstein condensation of molecules whose size is tiny compared to the interparticle spacing. And it turns out that both these limits are very well understood. But in between is a terrible, strongly interacting regime where C naught if order KF inverse. And now a lot about that is also understood, okay, both experimentally and theoretically. And so there's this review of us, you can look at it to see that. So if you apply the story to the 2D ultra-cold atoms, then this is what you get, that this is the BCS answer. Okay, you can see that the BCS answer is the, so of course in the coupling limit it is TC, but otherwise it's just some scale at which pairs form. But this is the BBC limit answer. Okay, so this of course came from a Russian. Double logs only come from Russia. Okay, so it slowly goes to zero. That it must go to zero in the extreme BC limit, all of you know, because in your graduate school or somewhere you showed that in 2 dimensions, the non-interacting boson BEC is zero, unlike in 3 dimensions. Okay, but interactions make it non-zero. So these are the 2 calculations. This is our bound, and the blue curve is a guess, okay, which we made in 2019, and this is from a 21 paper. So we felt, based on all the arguments given there, that our bound may be saturated in this very strongly interacting regime. Now, many years later, people did some very serious Monte Carlo and found that actually within error bars, our bound is saturated in this strongly interacting regime. But this is still Monte Carlo, okay? What about experiment? So there was an experiment 2 years after our paper in this amazing group. Yoshi Iwasa has been working for years on ionic liquid gating of superconductors. Okay, so he took this. So what was his idea? He wanted to see a BCS-BC crossover in a solid state material. Now, of course, we can't really tune the attraction. His idea was, okay, what we don't tune the attraction, we really need to only tune the ratio of delta over EF. So let me tune not delta, but EF. But in a metal, you can't even tune EF. But in a lightly doped insulator, you can, okay? So he took a 2-dimensional band insulator, which is zirconium nitrochloride, and he tuned the density over 2 orders of magnitude using intercalation with lithium and ionic liquid gating. And he found the following result. He found the remarkable results, again on the Uemura plot. Let's see, he's changing the Fermi temperature, which is proportional to the density in this 2D system, by more than 2 orders of magnitude. And this is quite a high transition temperature. It's around 20 Kelvin for this very low density system. But it comes and just saturates on our 1A bound. This is the parabolic system where our bound has been experimentally tested. Yes?
With the Fermi temperature, he just calculated the density of state by
That's right. He knows from the band structure what the effective mass is. maybe he has some measurements of the effective mass from quantum oscillations. I don't remember off the top of my head, but he takes that, he knows the density, he knows the, yeah, okay. But you should look at his paper. Okay, so far so good for parabolic bands. Now, what happens when you have non-parabolic dispersion? Because then what happens? Okay, so the first thing we did was at this point to check against numerics. Okay, so let's take the attractive Hubbard model, which has a non-parabolic. It's a cosine kx plus cosine ky dispersion. It's square lattice dispersion. You can do sign problem 3 quantum Monte Carlo. Okay, and this is the Berezinski-Kosterlitz-Thouless temperature as determined by Nandini and collaborators on this system as a function of the attractive interaction. Okay. This is the BCS answer, okay, with its essential singularity. Clearly, this temperature has nothing to do with that temperature. Okay. Now we can ask, what does our bound say? And it turns out this is what our bound says. So our bound actually gets the t squared over u asymptote of the strong coupling regime. But you can see here that in the weak coupling BCS limit, our bound is an upper bound, but a very useless one. Okay, but our bound is much more reasonable because BCS theory would have given you an answer up there near the maximum and all the way down into the strong coupling regime. So one of the sort of, what should I say, takeaway messages is if you can't do some complicated quantum Monte Carlo, just do mean field theory, use our bound, and the actual answer must lie below both of them. Because in some sense, mean field theory is also a bound. Because any mean field theory overestimates order, and therefore actual DCs are lower than that. So the bound is useful away from the BCS limit, where mean field theory fails. Now we can ask what happens when we come to non-parabolic dispersions in real materials. And here we looked at monolayer iron selenide on STO. This is a very ill understood material because in the bulk it has a 10 Kelvin TC. But when you make a monolayer, your TC is around 65 Kelvin. There's one report of 109. Outlier. Okay. We don't know what the pairing mechanism is. But the nice thing is our bound is agnostic about pairing mechanism. So let's see what can we say about this. So what we do is we do some K dot P perturbation theory for these systems. We fit the parameters to RPES and we just plug it into this and we get numbers. Okay, so I don't know if this is a good estimate or not, but it's definitely an upper bound on this without knowing anything about the mechanism. Okay, that's the key. Okay, that this band structure cannot support TC, which is this. Now let me ask the following question. I had said that our bound is related to the optical spectral rate. And the optical spectral rate has an inverse mass matrix that I can get from band structure, but it also has a density matrix, which is the fully interacting density matrix. Now, it turned out that in all the problems I showed you earlier, we didn't need to face up to it and things worked out. But in general, we don't know what to do with this. So we can do some mathematical physics. What we can do is use triangle inequalities plus the fact that D tilde is positive definite. That's the second law of thermodynamics. We can introduce some inner product in the space of operators and use a Cauchy-Schwarz inequality. Then we can say, I don't know what C dagger C is, but I can bound it by the square root of the occupation, the momentum distributions. Then I can say, I don't know what the momentum distribution is, but in a Fermi system, the momentum distribution can only be less than 1. And if I play such games, what I'm doing is I'm always keeping the inequality in place, even though I'm making the inequality worse and worse and worse. This is a game that mathematicians play just to get something without any approximations. Okay? And you get a rigorous bound on D tilde and therefore on TC just by looking at the eigenvalues of the inverse mass matrix. So you tell me a band theory and I can tell you without any approximation what the answer should be. There are other things we can do, but let me not dwell there. So now let's try to apply it to magic angle twisted bilayer graphene. So we took the tight binding descriptions by Koshino et al. Of Kang and Buffett to the continuum modular Bistrisker and McDonald. And you can use these rigorous bounds or you can make crude approximations and you can get numbers. But here there is a problem. Okay, so here there's a multi-band system which there's a problem. And the problem is the following, that the assumption that the interactions do not couple to the interaction term in the Hamiltonian does not couple to the vector potential is questionable in general for topological flat bands. Why is that? Because it's true, if you had, say, Hubbard interactions for all these bands, it would be fine. Or even electron phonon would be fine. But when you project down into the flat band manifold, the projected interaction looks very different and therefore can couple to the vector potential. So I would not trust these results so much. So that then led us to ask the following question. Can we actually get some exact results without making approximation for both trivial and topological flat bands? So that's what I want to turn to next, but maybe we can have a short break and you can ask me questions because it's a slight change, because now I'm going to talk about topology and so on. So are there any questions at this stage?
So okay, yeah. So assuming that the Debye energy is not the relevant Perry mechanism, essentially it means that you don't take electron phonon into account anymore. For
no, we can take electron phonon also into account. Everything I said works for electron phonons. I didn't assume that Debye energy. I just said I didn't make any assumptions about the interaction. Let the interaction be electron phonon. This is true. Now, if I know for a fact that the electron phonon is the relevant interaction, and if I know for a fact that Migdal-Eliashberg is okay because the small Migdal parameter, I can do better than this. Because if you build in more assumptions, you can get. What I told you is completely general. It's true for that system. But if you are willing to tell me what the mechanism is, if you are willing to tell me what the small parameter is, I can definitely do better. And people have done a lot of work on bounds within Migdal-Eliashberg. But clearly, cold atoms, there is no Migdal-Eliashberg. Or even these other problems that I showed you the slew of examples where these are clearly outside of the realm of this.
So I'll take the prerogative and ask a question
Yeah,
here.
please.
So you're looking back at this chapter of your talk, your entire methodology is based on calculating the stiffness, right?
Yes, and bounding it.
Bounding the stiffness. And then you're talking about two kinds of stiffness, one which is the DS and one which is the D tilde.
So D tilde is the bound of the stiffness.
So the focus here is how to calculate the D tilde?
Yes.
Yeah.
Yes. Because DS is hard to calculate. D tilde is easier to calculate. And D tilde is a physical meaning. It's the total optical spectral wave. If you can estimate that, you can't condense more than that into the delta function at the origin. That's the physical idea.
So there's something that connects today's talk and yesterday's talk when you're talking about the stiffness and the optical spectral wave.
Yes.
And these are, in my experience, things that come from very, very different worlds of physical phenomenology. So how do you intuitively connect superconducting stiffness and optical conductivity? Where do the two meet?
So the two meet in the following way. Okay. The stiffness you probably think of in terms of penny.
Yeah.
Okay? That's the response to a vector potential.
Yes.
And so the optical conductivity is the response to an electric field.
Okay.
That is also a response to a vector potential. And so theoretically, you can show that the delta function in the optical conductivity up to universal factors of 2 pi E H is the same ds that enter the derivation. maybe at a hand waving level, that's the best I can.
So then you allow yourself to focus on the calculation of the optical conductivity in all these systems, and
Actually, it doesn't matter. I'm just calculating the diamagnetic response. The tilde is a diamagnetic response. I talk about optical conductivity because it's intuitive as to for the bound. But if you want to think in terms of penetration depth, the diamagnetic response is a perfectly good way to think about the penetration depth also. It's interchangeable. The language that you use is not important. I'm calculating the stiffness, which could enter this experiment or that experiment. And stiffness is hard, but bounds on stiffness are easy, and they are useful. That's what I'm saying. I know.
I was curious about this Monte Carlo, the quantum Monte Carlo calculation. So when you have very, in the BCS regime, you don't worry about the bound, the new upper bound.
I mean, it's a bound, but it's
so
useless.
The question is, why is it physically becoming relevant as you move to a BC regime, right? So intuitively, that peak is getting smaller, I guess. That's what you're saying, the integrated weight under that finite omega.
So I think it's very easy to understand that intuitively also, okay? Which is the following. Suppose I am in the strongly paired regime. Suppose I go just for the sake of argument deep into the BEC regime, just for the sake of argument. Okay? I have bosons. They're condensed. I raise the temperature. The condensate is depleted. But the pairs are not dissociated. Because the normal state of a condensed Bose liquid is a uncondensed or normal Bose liquid. They're still bosons. So pairing persists till very high temperatures. Okay. And in fact, if you do certain analytic calculations, which I'm very happy to show you, this beam field TC over here, of course, has the standard BCS essential singularity. But in this limit, it goes to Saha ionization, which is the binding energy divided by the log of the binding energy over the Fermi.
It's just that the length scale is becoming smaller and smaller.
Yes.
Right? So this is why it's kind
But it's the energy scale. So the length scale becomes smaller and smaller. The binding energy is very large. Okay. So the stiffness kills you first. To actually dissociate the pairs, you have to go to much higher temperature of order the binding energy, but there's a logarithm which comes from Saha. Actually, Andre, I have to tell you this. I showed this result to Abrikosov many years ago in some other context, and he says, this is the Saha ionization equation. And I said, oh, I don't know it. He says, this was your countryman. You have to know his work. So, of course, these guys from the Landau school knew all of physics, astrophysics, plasma physics. So, I had never heard of it. But it's a very important thing in astrophysics and plasma physics, Saha ionization. Actually, semiconductor physics. Okay, anyway, there were other questions.
Actually, you answered it by answering the other question.
Okay, very good. Should we move on? Okay, so now I want to discuss black maps. Now, I'll go to the seemingly stupid limit of a completely flat band. This is a theorist one. Okay. In reality, interested biallegraphy, they're very flat, but they're not completely flat. But let's ask this question. And I'll ask the seemingly stupid question, how superconductivity develops there. Okay. Because I have no kinetic adhesion, which means I have a zero velocity for electrons. Because you see, if epsilon k is a constant independent of k, then d epsilon dk is 0. Okay. Now, two questions arise. The physical question arises, if the electrons don't move, they cannot conduct. So why are you asking the stupid question of superconductivity? Okay, that's the physical question which we need to answer. And there's a technical question that if you want to talk about superconductivity in terms of the superfluid stiffness or the delta function and the optical conductivity, you have to couple a vector potential. But the vector potential can't couple to the kinetic energy. I already said that. So if at all, you must learn how to couple vector potentials to interaction terms, right? Because that's the only way you're going to get a response, electrical, magnetic, whatever. So we have to answer both of these questions. So, but before I do that, the answers will depend in a very interesting way on quantum geometry and topology of the bands. So that's not something that perhaps many people are familiar with. So I'll have to do a one-slide review of that and then return to those questions. Okay. So first I want to remind you what a Warnier function is. Okay. So you have a block wave function in K-space, and you can Fourier transform it, and you get a real space Warnier function. This has been known for a very long time. It's the work of Warnier. But now there's a problem, because the block wave, this is the periodic part of the block wave function, I can actually multiply it by any k-dependent phase, and that's an equally good block state, right? But when I Fourier transform it, different choices of the phase give me very different Warnier functions. So there is nothing unique about the Warnier functions. This is very bad, because we want the Warnier functions to look as much as possible like atomic orbitals. Of course, they are orthogonal on different sites, but nevertheless, we want them as localized as possible. So in this very important work of Marzari and Vanderbilt, they actually wrote the Warnier 90 code also after that, which all band structure people use. But they did some very important perceptual work, actually, David Vanderbilt. They said that the thing you need to do is to maximally localize these Warnier functions. Okay, and so they define the spread of the Warnier function in the usual way. This is just R squared sandwiched between the Warnier functions, and they said to choose these phases so that the spread becomes as small as possible. Now you say that when you do Ashcroft and Mermin and tight binding, you're pretending that the Warnier functions are delta function localized. Why can't you always choose phases to squeeze them down to a delta function? And again, Marzari and Vanderbilt said, no, that's not possible. Okay? And what is the obstruction there? So they introduced something called the quantum metric, which was introduced by mathematical physicists, I think more than 100 years ago. So it's called the Fubini-Studi metric in that work. So this is a distance between two states in Hilbert space. Okay, so it's defined as follows. If you take two different states and you take their inner product, absolute value squared, if these two states are the same up to a phase, then this will be just 1. And so the distance between them will be 0. This makes complete sense. But if these two states are orthogonal, then the distance between them will be 1, which in this metric is the largest distance between two states in Hilbert space. Okay, and so if you look at nearby k points, then you have a small distance, and you can write this ds squared, and you can write it in the form of a metric tensor in case with k dk. Okay, and this metric tensor is what is called the quantum metric, which describes the quantum geometry of wave functions in Hilbert space. What Marzari and Vanderbilt showed, and so of course, as a metric tensor, it's a positive definite quantity. They said that the Marzari-Vanderbilt spread, or the Warnier function spread, is bounded below by the sum over the Brillouin zone, the trace of the quantum metric. So if there is a non-trivial quantum geometry, you cannot squeeze this down to 0. Okay, this will come in your way. This is the best you can do. So that's how quantum geometry is going to enter into our story. Now, actually, there's a connection between quantum geometry and topology. And the topology part is probably more familiar to young students these days. So there is something called the quantum geometric tensor, okay, which is a Hermitian matrix whose real part is symmetric and is just the quantum metric I introduced, and whose imaginary part is antisymmetric and is nothing but the very well-known Berry curvature. So there is a package deal object, quantum geometric tensor, that contains both the quantum metric and the Berry curvature. And in fact, there is a very well-known inequality connecting quantum geometry and topology, which says that the trace of the quantum metric is always bounded below by the absolute value of the churn. Yes?
I don't know whether I understand what quantities go into this G matrix. You mean it's independent of K, is it?
Yes.
But then it must capture the bands or something?
So this is trying to understand. See, what does Berry curvature talk about? It tells you basically how states are changing as you go from K to a neighboring K. That's so just that the Berry curvature captures one piece of it, the quantum metric captures another piece of it, which is less familiar to you, but that's what it is. Intuitively, at a one slide level, if you've never seen it before, that's the best way to understand. Distance between two single particle wave functions in Hilbert space. As you move from one point in K space to a neighboring point in K space, how much did the state change? By what distance did they change?
So it is different for systems with different band structure.
Yes, absolutely. Just as the Berry curvature is.
Yeah.
And even if the Berry curvature is zero, the quantum metric still exists, you know. So like even if you talk about Vanya functions for silicon, you still have quantum metric, even though there's no Berry curvature in such a system. Okay? Okay, now you also know, and I said this before, that if you have a churn number, that's a topological obstruction to making exponentially localized Vanya functions, and that's also going to be important later on. This result was proved relatively recently, actually, in the sense that Walter Kohn showed in the 1950s as a postdoc that in one dimension you can always find exponentially localized Vanya functions. And for 50 years, people tried to prove this result in higher dimensions and failed because they didn't understand topology well enough. But once they did, they realized that actually there's a topological obstruction and you need to make certain assumptions in order to get it. Now, this was a detour because these ideas are going to be central to what happens next to the exact results I show you. Okay. Maybe I should keep an eye on the clock.
11, it's 10 past 11. So.
Okay, I'll be done in maybe 20 minutes or so. Half an hour. Not half, 20 minutes. Okay, so now come back to superconductivity in flat bands. So there was pioneering work done by Pavi Torma, who did a BCS mean field calculation for a flat band superconductors of an attractive Hubbard model in completely flat bands. And she and her colleagues showed that the mean field superfluid stiffness is U times the trace of the quantum metric. So that's where the quantum metric appears. And you will get an intuitive feel for why the quantum metric appears very soon. Okay, yes?
Is this true for all cases or just for flat bands?
This is true only for the attractive Hubbard model with flat bands. Okay. It's a very special result. Now, the first question is mean field theory valid when the interaction is infinitely larger than the band, which is zero? We don't know. Right. The second question is a more technical, nuanced question. They also made some further assumptions, but in general, it's not clear that this assumption is valid. And then the final thing is that there are a lot of claims in the literature that you can use this to provide a topological lower bound of the stiffness, and these claims are completely false. So let me explain why, because they're going around a lot. Okay. So yes, this is the mean field result. And yes, I told you that this object, okay, I should put an absolute value here too, is that trace of the quantum metric is bounded by the Chern number. Okay. So therefore they said, look, the mean field stiffness is bounded below by the Chern number. But you see, the thing is, mean field theory neglects quantum and thermal fluctuations. Therefore, any mean field stiffness will always be greater than or equal to the real stiffness. Yeah, does that make sense? So now you cannot combine these two inequalities to provide any lower bound, topological lower bound on the real stiffness. And there are many counter examples which show that these topological lower bounds are wrong. Okay. So now let's ask ourselves, we have all these ways of finding rigorous bounds on the stiffness. Can we actually find rigorous bounds which are quantum geometric in nature? That's the question we asked. Okay, so what are the challenges? So you take some model, which is a multi-orbital model, and again, because actually for more complicated interactions, nobody knows how to do these calculations. People have tried and it doesn't work out simply. So we'll also take an attractive Hubbard model on flat band or a very nearly flat. Now, if you take the full model, then we can just use all the results we had derived earlier to get us an upper bound at the stiffness. No problem. Okay, without quantum geometry, without any of the other stuff I've talked about. The problem is that multi-band bound, which was derived in the first part of my lecture, is highly suboptimal. It involves optical spectral weight to go to higher bands, which is totally irrelevant. Because actually, it's only the intra-band optical spectral weight here that should really contribute to the stiffness if the interaction is much smaller than the gap to other bands. Okay, so we need to find a better bound. Okay, so we need to find something that involves only intra-band or low frequency spectral weight where you actually just go over the flat bands. That's what I call the low frequency beat rather than the full beat. So here's the strategy. We'll project down to the subspace of flat bands. We'll find a low energy effective Hamiltonian in this projected limit, find its coupling to an external vector potential, and then compute d tilde low. First, we'll do that for trivial flat bands, and then we will add topology. So trivial flat bands. So let's look at the attractive Hubbard model on the Lieb lattice. So Lieb lattice is some very famous lattice that Elliott Lieb introduced, and if you stagger it by changing the hopping between these two, you can actually get an isolated, completely flat band, which is separated from the other bands. And we will study situations where the attraction is much smaller than the gap to other bands. That's the interesting limit. And the chemical potential lies in the isolated flat band. So we do all of this. Now, I'm not going to take you through the algebra, but the essence is easy to understand. When you project into this low energy band, you have a situation where the attraction is very large compared to the band bandwidth is 0. So you get tightly bound pairs because you have to satisfy you. You are not paying any kinetic energy cost for bringing two electrons very close together. Okay? Now, what happens is, even though single electrons couldn't hop, it turns out that the pairs can hop. That's a very counterintuitive but correct statement. Okay? So why does that happen? The reason why it happens is the following, that when I say you form tightly bound pairs, you don't really form them on site. You form them in the Warnier function of that flat band. And the Warnier function from here can connect to the Warnier function to the next site. And as a result, you can find, and the Warnier function cannot be localized as much as you want because of this quantum geometric obstruction. Okay. So the pairs are mobile, even though single electrons are not. And we can use gauge invariance in very detailed form to compute how the vector potential couples to this low energy effective Hamiltonian.
Yes. The pairs are mobile because of the geometrical constraint on the Warnier.
Yes.
But why does this constraint not work on a single electron?
So this is a very subtle point which I really don't know how to wave my hands on. What we need to do is to write down the low energy effective Hamiltonian. This only has 4 Fermi terms, C dagger, C, C dagger, C, or C dagger, C dagger, C, C, right? No kinetic energy. Now, in these, I'm giving you a theorist out, it's not hand waving. Now, the thing is that what can happen is that when you put an external vector potential, actually you pick up a phase with a 2e in the vector potential, because a pair can hop through. Because C dagger, C, C can amount to destroy a pair here, create a pair there, destroy a pair. And the way in which this works involves the Wannian functions. I can try to give you a better feeling.
So say if you do that C dagger C,
there is no C dagger.
It doesn't work, but
yes.
C dagger this.
Yes. Yes, it's very, very curious. Okay. Okay, and so we get upper bound on the stiffness, which is now very intuitive to understand. Stiffness is an energy scale. The only energy scale is U. There's no other energy scale in the problem. Stiffness must vanish when the flat band is completely filled or completely empty, because then it's a band insulator. So we have an N tilde, which says it vanishes when either the flat band is completely filled or completely empty. Okay, and then the stiffness or all transport occurs only because of the spread of the Wannian functions. So, and that is bounded by the trace of the quantum metric. So we have a quantum geometric upper bound. Now, we can only compare it to mean field theory, but let's not worry about that. I want to say something very important. Look, I told you that take this TC over epsilon Fermi as 1/8 bound. It's very interesting, but if you try to use a parabolic band to describe a flat band, you fall flat on your face. Okay, why? Because if my chemical potential is here, and you can make it half filled, we all agree epsilon Fermi, we should call it 0. So, but this system has a finite TC. Okay, so TC over epsilon Fermi can be infinite because epsilon Fermi is a very ill-defined. Okay, but our optical spectral rate sum rule is perfectly fine and completely well defined, even in this system, which is infinitely far from a parabolic. Okay, the finite TC is actually guaranteed by Lieb's theorem, because Lieb invented this Lieb lattice to prove that the repulsive Hubbard model and the Lieb lattice has ferromagnetic long-range order at 0 temperature, and others immediately used it using some particle-Wood transformation to prove that for the attractive Hubbard model, Lieb's theorem guarantees off-diagonal long-range order at 0. Actually, it turns out we can stand on Lieb's shoulders and prove some lower bounds too, but let me not discuss that. Okay? This uses some very tricky things about Lieb's theorem. So we have upper and lower bounds, which are quantum geometric. Now, topological flat bands. So now we have a problem. Okay, so we'll take a model, which is also an attractive Hubbard model, but we have nearly flat bands with a Z2 topology. So basically, we have a flat band. In this model, SZ is conserved. So there's one flat band with spin Chern number up equals +1, another flat band with spin down Chern number -1. That's what it is. It's a time reverse. Then it's situation. Now the problem is we can't do what we just did on the previous slide, because if you have topology, then it seems like the Wannian function spread will be infinite, diverges. So we don't get any useful. Everything is less than infinity. It's not a useful answer. Okay. So what do we do? So actually, again, here Vanderbilt comes to our rescue. So we can adapt some work that he did, which says that you can unwind the topology. You have two states, a low energy up state and a low energy down state with opposite Chern numbers. You can find a very cunning linear combination so that both of these have Chern number 0. The question is, how did you evade the topological obstruction theorem? And you evaded it because here the two states are related by Cramer's degeneracy. But here, time reversal is actually implemented in a slightly strange way. It's time reversal times sublattice interchange. So it's slightly non-local, and that allows you. Okay, let's not worry about this. So here, actually, we can again find quantum geometric bounds. And here we can even compare with Ehresberg's quantum Monte Carlo, and somewhat embarrassingly, our bound falls right on top of quantum Monte Carlo, but that's a separate story. Let me not discuss this experiment. I think time is up, except to say that here again you see in twisted bilayer graphene, KFC is extremely small, 1 to 10. And again, TC over EF can be very large because there is no TC over epsilon Fermi bound when you have nearly flat bands, or actually even if you have Dirac dispersion, you don't have such a bound. It's only for parabolic bands or something which is close to parabolic bands that we have set down. Now let me come to this final question. If I did all these wonderful things in 2 dimensions, why did it not work in 3 dimensions? If it had worked in 3 dimensions, maybe you have disallowed me to talk in the TIDES conference. So, but I'm unhappy that it didn't work in 3 dimensions. Okay, so let's answer this question. So the experiment seems to suggest that there are many 3-dimensional materials which all lie below some bound. So why did it not work? Now I already told you that in ultra cold atoms, we know in 3D that the maximum observed TC is 0.22, which is higher than the 0.12518 that I found in 2D. But we know this number only from experiments and from quantum Monte Carlo. We do not know this number from any kind of analytical bound that I showed you. So this is a hard problem. First, let me ask you the following question. Bogoliubov solved the Bogoliubov-Bose gas in what, 1947? Something like that. Andrei Varlamov. Bogoliubov-Bose gas, 1947?
Repeat, please.
Bogoliubov dilute Bose gas?
1947.
1947, right? But for 50 years, we didn't know the answer to the following question. Is the TC of the dilute Bose gas equal to the non-interacting BEC, TC? Greater than or less? It's a very simple question. Okay. So 50 years after Bogoliubov, we did not know the answer. And a lot of famous people gave wrong answers. Feynman said that because of interactions, TC decreases. Lee and Yang said it changes but refused to commit to the sign of the change. Fetter and Balachka, which is a standard textbook, says that TC decreases. It's all wrong. Okay, now we know that TC increases. Okay, we can discuss why it took so many years. That's a separate thing. The reason I bring this up is that experimentalists often draw a BEC line and pretend that that is also an upper bound. The limit in 2D is our line for parabolic dispersion. BEC, but BEC is really not anyone's 3D bound. Okay? So non-interacting BEC is not an upper bound on TC. That's firmly established. Okay, then you could follow Emery and Kivelson and say that let's look at thermal phase fluctuations. So now our bound, the optical spectral weight on stiffness is valid in all dimensions. The difficulty is in connecting stiffness to TC in higher than 2 dimensions. Because as Emery and Kivelson pointed out, there's something very special about 2 dimensions. 2 powers here, 2 powers here cancel out. ds has units of energy, and you get the universal pi over 2. In 3 dimensions, you have 3 powers here and 2 powers here. So there is some cutoff. And they discussed what that ultraviolet cutoff should be. But now we have no way that we know of to bound this non-universal C in 3D. Okay? And finally, quantum phase fluctuations in 3D also create trouble for us. So of course, we would like to know how high TC, all of us experimentalist theorists, how high can TC go? But if you want to prove a theorem, it should also work when TC is very low near a quantum phase transition where TC vanishes and ds vanishes. So at such a quantum phase transition, there's some very general scaling arguments you can make to show that TC and the superfluid stiffness are related near a quantum critical point in a universal way where Z is the dynamical critical exponent and D is the spatial dimensionality. Magic about 2D is it enters here and independent of the dynamical critical exponent, this relationship between TC and ds holds. In 3 dimensions, it says that TC must go non-linearly and Z must be greater than or equal to 1. So this scaling must fail near a 3D quantum critical point. And if you think this is just some theorists doing mumbo jumbo, actually this is seen in experiments. Okay, so this is data I took from Lemberger, but similar results appear from the UBC group and from Kozovic, that if you look at thick films of Lemberger or Bond and Hardy single crystals in underdoped YBCO, TC scales like square root of DS. Doesn't scale like as you underdope strongly. Okay, so this is consistent with 3D quantum criticality. This C equals 1. As opposed to his very thin 2-unit cell thin films of Lemberger's where TC scales like DS. Okay, so if TC scales like square root of DS, I don't know how to prove any of this. So those are the challenges. Okay, we have to overcome these challenges. We don't know. We meaning as a community, we don't know how to do that. Okay, so let me just leave you with these references, and that's the end of my talk. Thank you very much.
Don't we go again into a long discussion to say that returning back to the phase transition issue?
Yes.
I mean, we all learned that the phase transition has to do with an order parameter. Superconductivity, the order parameter is dead. So,
but you have to. So yes.
The other thing is that we're changing a state of matter from Cooper pairs, from bosons to fermions.
So let me answer all of this. This is not a. We should go into this long discussion because I think this is a fundamental discussion which has nothing to do with details of any calculation that any theorist does. So it's very important. So first, let's talk about pairing. Is that a fundamental phase transition? I gave you the example of hydrogen molecules dissociating into hydrogen atoms. Is that a phase transition?
No, if you change the nature, you change the statistics of the particles, right? You go from fermionic to bosonic in the case of superconducting.
You see, you have to be very careful about like, what experiment can you do to check for the statistics and so on. But I'm asking a very simple question. If I take hydrogen molecules and I heat the temperature, heat it up, eventually it will dissociate. This is extremely well known.
But do you agree that delta is the order parameter of the...
No, wait, we discussed order parameter. Abhiyal, one thing at a time. You said pairing. So I'm giving you, we'll discuss order parameter also. We can write down all the topics we'll discuss, but let's first discuss this.
That's why you said I don't think you should do it now, just raising the question.
No, I think people should hear it. I mean, we can do it in Q&A if you want. Because this is a very important thing for the students to hear this. Right? I don't think dissociation or unbinding is.
You don't think moving from a fermionic system to a bosonic
system? Let's first discuss
fermion boson. Okay, I'm willing to discuss the dissociation of it.
Yeah, so let's discuss this.
It's a molecule. Right?
Yes.
And you have to find the energy.
Yes.
And it relates one molecule A to one other A to another A, right?
Yes.
And it constrains the relative motion of both.
Yes.
Right? So when it dissociates, I don't know how you call it, changing something like important the position.
You are.
Right?
But that is like saying when you go from night to day, is there a phase?
I have another comment on it. Can I?
This isn't fair.
So
this is the real.
Can I just add one sentence? So no, I have a different view on this.
Yes.
So I would say that dissociation means moving along the Lennard-Jones potential.
No, that's a description.
I mean, what I mean is there is nothing phase. I mean, for me, it's not a phase transition because both thermodynamic function has a singularity or non-analytic.
Exactly, it has nothing to do with Lennard-Jones potential. It's a statement that it's a smooth crossover. The two states of matter may be very different, but it's a smooth crossover. Like for instance, liquid to gas, you can always go around the critical. And so the thing is, some states of matter, they may look extremely different, but there's no phase transition between molecules and atoms. There's no phase transition. So we have to bear that in mind, that just because some things look very different to us, they may have very different properties, that does not necessarily make it a phase transition. So what makes something a phase transition? That's the next question we can ask. Yeah, please.
I will not be courageous and ask a very stupid question. what is generally understood to be a phase transition? In my mind, what I remember is that a phase transition is anything where you can define an order parameter, which is 0 at one side of the phase transition and non-zero at the other side of the phase transition.
Very good.
Is this the correct definition?
Yes, for most phase transitions, but for the costless harness phase transition, it's a bit tricky. Because now you don't have long range order, you only have algebraic order at any finite temperature. So we need to worry about that too. But if you're willing to stay away, so let's say we stick to 3-dimensional systems, okay? Then what you say is how we understand every phase transition.
Then I want to ask if I just define the number of hydrogen 2 molecules as a phase parameter.
Yes.
Is then not the dissociation a phase transition?
No, because it changes smoothly.
But there is a point where none of them are H2, and then there's a
Then
point
slowly you have more, and slowly you have more, and slowly you have more. There's
No, but
nothing.
continuity is not the proof of, the second order transition are smooth, right?
No, all phase transitions that we know of show a singularity. That's a definition.
The order parameter is good, but the derivative is not.
Yeah.
There is a
So there is a singularity in it.
But when the order parameter delta goes to 0, that's a phase transition.
So the thing is, look at this example. What fraction of molecule is dissociated? At low temperatures, the fraction is 0. At very high temperatures, the fraction is 1.
You're avoiding the points.
No, I'm not avoiding the point.
Because it's not an order parameter.
So he said it. Let's make it an order parameter. I'm saying it cannot be an order parameter.
Well,
so I'm not avoiding. I'm answering his question. Yeah. Okay. Now let's ask. Let's ask the other thing. You want to discuss order parameters. Okay. Let's discuss order parameters. Order parameters can be quite difficult to measure. Okay. For instance, in helium-4, it's very hard to measure the order parameter. You can now do heroic neutron scattering to find how many bosons are in the condensate, but it's not an easy experiment to do. Or in superconductors, okay, other than Josephson effect or something, it's very hard to measure the order parameter per se.
Delta is the amplitude of the order parameter, so it's easy to measure the gap.
That is not a good definition, because if the phase of the order parameter is random, or the phase of the local order parameter is random, there is no order parameter in this case. Avya, this is extremely important. It's not okay. It's not okay. It's not because I say so. This is extremely important point. I'm not trying to win an argument. I'm trying to explain something actually here.
So what is the order parameter in your definition of superconductivity?
So in my definition of superconductivity, the order parameter, which is extremely hard to remember, is the following. It's not my definition, it's C and Yang definition, okay, or Landau-Ginsburg's definition. Not that. So there's this very classic paper of C and Yang in Reviews of Modern Physics called Uptiring Long Range Order. So for both systems, the order parameter is for helium. Superconductors, it's the order parameter. The IC model for a magnet. That's a magnet. That's the order parameter. In every case you can write down.
A bunch of numbers and letters. It's a bunch of letters,
So, bunch of letters. But that's how physics is understood, bunch of letters. Because we give physical meaning to those bunch of letters. This is the magnetization. This is the condensate fraction. This is whatever you want to call it. No, but it is. So now we can ask what the experimental observations are. We can come to that. But so first, the existence of the order parameter is you look at some correlation function, equal time, and you ask whether it goes to a finite value at long distances. So I'm always looking at some operator correlation function and asking how it decays in space. And I'm saying if it goes to a non-zero value, I call it the order parameter square. This is that's so there's a physical meaning to this order parameter, because then there's a susceptibility associated with the order parameter. There's a correlation length associated with the order parameter. There's physics associated with the order parameter.
So if you go to the example that we got before here, the population of dissociated molecules, so why does this not fit this particular?
Okay, because I'll tell you, this order parameter always goes to zero like this. It could be some other parameter, but as a function of this. Singularity at a second order phase transition. If it's a first order phase transition, it can jump up. At crystallization, for instance, it will jump up. The fraction of dissociated molecules goes from 1 to 0 like this. No singularity as a function of that. Yeah, it's whatever it is. Yeah. So I think you need a singularity. Now again, I'm telling you that costless Thouless lies outside this discussion. Okay, so we can come back to that. I mean, you have to be subtle because I can't include that in this because this is not what happens in costless Thouless. We can discuss why. But another way to say it is the follows. These are hard to measure, but response functions are much easier to measure. Why do you call something a solid? Because you kick it and you feel it. So, or you measure a shear modulus in a solid, and you say this is a solid. Liquid, you don't have to go to some neutron source and be that. Okay, so you know what a solid is and what a liquid is. So response functions are a very good way of looking at everything. In superfluid helium, you can do these Andronikashvili torsional oscillator experiments to measure the superfluid. Okay, here you can do either two coil measurements, a kinetic inductance, or other measurements to measure the superfluids. That's a response function which shows a singularity. In hydrogen molecule case, there's no response function that shows any singularity as you change parameters ever. But you're not convinced? Okay.
There should be adjourn. Okay. So thank you. Yeah, please.
You've already answered this. Should the order parameter always be an observable?
It can be a very difficult observable. In principle, it is observable. But like how many bosons in the condensate is a very difficult observable. Whereas measuring the superfluid density, superflow, is the easy observable. In superconductors, measuring the order parameter is a very difficult observable. But how many, what is the stiffness of the condensate is an easy observable. In a ferromagnet, the magnetization is an easy observable. Okay? In an anti-ferromagnet also, it's not that easy to measure the Niel order parameter. It won't stick to your refrigerator like a ferromagnet. Yeah, so in principle it is, but whether the experiment is easy or hard depends on the context.